Hello everyone, and welcome back to ILTA Physics Online. Today, we're going to study the force that pulls everything toward Earth. In other words, weight. In everyday life, we often use the word weight, but in physics, it's actually different from mass. We can even distinguish it from what we call apparent weight, which is the weight we feel when an object is moving. In this lecture, we'll first look at the physical definitions of mass and weight, and then we'll talk about apparent weight, what we actually feel in daily life. We'll also learn about weightlessness, a special condition that occurs in certain motions. And finally, we'll discuss the unit pound, which is commonly used in daily life but closely related to weight. All right, let's get started with the force created by gravity, weight. Let's briefly review what we learned last time. So far, we've studied two separate branches of physics: kinetics, which deals with forces, and kinematics, which deals with motion. When we combine them, we call it dynamics. These two areas are quantitatively connected by Newton's second law, the law of acceleration. To solve dynamics problems, we first draw a free body diagram to analyze the forces acting on an object, separating them into horizontal and vertical components to find the net force in each direction. Because motion in the horizontal and vertical directions are independent, we can analyze each one separately. The horizontal force only affects horizontal motion, and that relationship is expressed as F equals ma in the x direction. Likewise, vertical forces only affect vertical motion, and again, the relationship is F equals ma in the y direction. So to summarize, we can simply apply F equals m separately to the horizontal and vertical directions. Make sure you remember one for the horizontal direction and one for the vertical direction. Finally, we also studied one of the most basic states of motion, equilibrium. Equilibrium means that an object is either at rest or moving at a constant velocity. In other words, there's no acceleration. According to the law of acceleration, if acceleration is zero, the sum of forces in both horizontal and vertical directions must also be zero. So, most two-dimensional dynamics problems are solved using Newton's second law, by setting the sum of forces in each direction equal to the object's mass times its acceleration in that direction. Now, let's study the relationship between motion and forces in terms of mass and weight. First, let's clearly distinguish between the physical definitions of mass and weight. Mass is a measure of how heavy something feels, more precisely, in physics. Mass is defined as the amount of inertia an object has. The inertia means an object's tendency to resist changes in its motion. It may sound a bit abstract now, but we'll look at it more closely later. Intuitively, an object's mass never changes, no matter where it is or what forces are acting on it. That means an object's mass is the same whether it's on Earth, the Moon, or anywhere else. And it also stays the same whether the object is moving or not. In contrast, weight is the gravitational force acting on an object, the force with which the Earth pulls it downward. Since weight is a force, it's a vector quantity, because it's a force of attraction between two objects. For example, between the Earth and the object, the strength of that force depends on the planet's gravitational acceleration. That means an object's weight will be different on Earth than on the Moon. So, as you can see, mass and weight are not the same thing. They represent completely different physical quantities. But they're related by Newton's second law, the law of acceleration. If we apply the formula F equals ma, and substitute the gravitational force, W for F, and the gravitational acceleration, G for A, and we get weight equals mass times gravitational acceleration. This is an equation you'll use over and over again in two-dimensional motion problems, so make sure to remember it well. Alright, let's learn about the apparent force next. Earlier, we said that an object's weight is the downward gravitational force. That means, unless we change planets, say from Earth to the Moon, the gravitational acceleration and therefore the weight stay the same. However, gravitational force is difficult to feel or sense directly. So instead, we usually sense an object's weight indirectly using a contact force. Those kinds of forces usually show up as a normal force or as friction. As you can see in the figure on the right, when you stand on the ground, you feel your weight through the soles of your feet where you're in contact with the ground. Physically speaking, the ground pushes upward with a normal force, and that's what you perceive as your weight. If you were hanging from a rope, you would feel your weight through the tension and friction between your hand and the rope. We call this the apparent weight, and it usually appears as a normal force or a friction depending on the situation. Interestingly, apparent weight can change depending on the object's motion. For example, when you ride a roller coaster and go down a steep slope, you might feel like you're floating. That's an example of weightlessness. On the other hand, astronauts during rocket launch feel much heavier. That's also an example of changing apparent weight. Let's now analyze these situations physically. First, let's look at apparent weight when an object is in equilibrium, that is, at rest or moving at constant velocity. If acceleration is zero, then according to Newton's second law, the net force acting on the object must also be zero. When we break this down into horizontal and vertical directions, the net force in each direction turns out to be zero as well. For example, when a person is standing still on the ground, two main forces act on them: the gravitational force downward and the normal force upward. Let's assume we set up a standard XY coordinate system to analyze the forces in motion. The normal force is upward, so we call it positive n. The gravitational force is downward, so we represent it as minus wg in the equation. We knew that the apparent weight is represented by the normal force n. Since the person is in equilibrium, acceleration equals zero. The sum of all forces is zero. Therefore, n equals wg. So, in equilibrium, the apparent weight equals the actual weight, which is mass times gravitational acceleration. Just like in the previous example, even when you're hanging from a rope as shown in the picture on the right, the normal force and the weight still act in opposite directions with the same magnitude. Therefore, the apparent weight equals the actual weight in equilibrium. If you understand this explanation clearly, you're doing great with two-dimensional motion problems. Now, what if the object is accelerating? For instance, imagine you're in an elevator that's accelerating upward. We can apply Newton's second law again. F equals ma in the vertical direction. The net force in the vertical direction equals the object's mass times its vertical acceleration. In this case, since acceleration is upward, it's positive. We can set up the equations the same way we did before, taking into account the directions of the normal force and the weight. Then we find that the apparent weight, represented by the normal force, is greater than the true weight. That's why you feel heavier when the elevator starts moving upward, and the faster it accelerates, the heavier you feel. Now let's think about the opposite case: the elevator accelerating downward. The net force equation looks the same, but now acceleration is downward, so it's negative. When you solve it, you find that the apparent weight is less than your actual weight. And again, the greater the downward acceleration, the lighter you feel. So in both cases, Newton's second law explains exactly what we experience physically when the elevator goes up or down. What's fascinating is that apparent weight isn't just a feeling, it's a measurable physical quantity. If you stand on a scale inside a moving elevator, the reading on the scale will actually change depending on the elevator's motion. It'll go up when the elevator accelerates upward and down when it accelerates downward, since the normal force actually exists and acts on a scale. Now, what if the downward acceleration keeps increasing until your apparent weight becomes zero? That's what we call weightlessness. Physically, weightlessness doesn't mean there's no gravity. It means your apparent weight is zero. If we express that mathematically, setting apparent weight to zero and combining it with Newton's second law, we find that the condition for weightlessness is when acceleration equals negative 9.8 meters per second squared. In other words, when an object accelerates downward at 9.8 meters per second squared, the same as free fall, it experiences zero apparent weight. The picture on the right is a classic illustration of a zero-gravity situation, usually showing an astronaut floating around inside a spaceship. So, if they're experiencing weightlessness, does that mean these astronauts are in free fall? More precisely, like in the elevator example we talked about earlier, is the spaceship itself in free fall, making the astronauts inside feel weightless? The answer is yes. This is what we call orbital motion, which is basically free fall motion along a circular path. The spaceship is in free fall, and that's why the astronauts inside experience weightlessness. We'll study the details in the next chapter. Consider this a brief sneak peek. Now finally, let's take a look at the pound, a unit we commonly use for weight in everyday life from a physics perspective. It's similar to what we learned today about the relationship between mass and weight. The pound that we use in everyday life is actually a unit that can represent both mass and force, that is, weight. To be more precise in physics terms, we need to distinguish between pound mass, or lbm, which is used as a unit of mass, and pound force, or lbf, which is used as a unit of force. First, pound mass, or lbm, is a unit of mass like the kilogram, representing the intrinsic mass of an object. As shown in the relationship below, 1 pound is equal to 0.4536 kilograms, and 1 kilogram equals 2.205 pounds. On the other hand, pound force, or lbf, is used as a unit of force and is defined according to the definition of force: the gravitational force acting on a 1 pound mass object on Earth. In other words, according to Newton's second law, 1 pound force can be calculated as 1 pound mass multiplied by the gravitational acceleration, 9.8 meters per second squared, which equals 4.448 newtons. These are the two specific definitions of the unit called pound. Then, why do we often confuse the pound as a unit of mass and weight in everyday life? The reason is the definition of pound force. According to its definition, 1 pound force on Earth corresponds exactly to 1 pound mass as shown on a scale. And, in general, the pound in the narrow sense in physics refers to the unit of force, pound force. Since we studied mass and force, that is, weight, in this lecture, I explained the pound unit. Through today's lecture, we studied mass, weight, and apparent weight depending on the state of motion. When the apparent weight is zero, that is a zero-gravity state, which can be understood as the apparent weight felt by an object in free fall. That's all for today's lecture. Great job, everyone.